Okay, welcome back to McNab Chemistry. Today I'm going to do the first of my green pen pages, where we have a look through some questions that have recently been completed and look at some of the common errors that took place. Okay, the topic this week was redox Group 7 and Group 2, and these are some of the common errors that took place. Here are my green pens, but you'll notice that I write in black because the green pen doesn't show very well on the camera. So there you go, let's move those aside. Right, okay, let's have a look at question 2 to start with. Okay, it says, in an acidified aqueous solution, nitrate ions, NO3 minus ions, react with copper metal, forming nitrogen monoxide, NO, and copper 2 ions. Okay, write a half equation for the oxidation of copper to copper 2 ions. Okay, so let's just do that. Cu going to Cu2 plus 2 electrons. It tells us what's happening, we just have to write the equation. Okay, then write a half equation for the reduction in an acidified solution of nitrate ions to nitrogen monoxide. Okay, so NO3 minus going to NO. Well, straight away you notice that I haven't got enough oxygens on my right hand side, so with all of these half equation questions, when there's not enough oxygen on one side of the equation, we add water. Okay, so I've got 1 oxygen there, I've got 3 there, so I need 2 waters, 2 oxygens. Okay, when I introduce my water on the right hand side, that creates 4H plus on my left hand side, and then I balance my left hand side so that the overall charge is 0 by introducing 3 electrons, 3 negative charges. Then my right hand side, the overall charge is 0. Okay, right, so these are my 2 half equations, and I need to combine those, don't I? So I just look at my electrons and I see that there are 2 electrons in the first equation, 3 in the second. Okay, well, I need these to balance. Okay, so surely if I multiply that first equation by 3 and I multiply this equation by 2, 3 times 2 is 6, 2 times 3 is 6, everything will balance, and that's exactly what happens. Okay, so we end up with 3Cu plus 2 NO3 minus plus 8H plus goes to 3Cu2 plus 2NO plus 4H2O. No electrons on the left or the right because they balance. Okay, perfect. There you go. Okay. Yeah, the next common set of errors was all based around the halide, the silver halide solubility in ammonia. This is an area that really mustn't be missed. Right, so let's have a look at part C here. Question 3, part C. Medicines for the treatment of nervous disorders often contain calcium bromide. Okay, so I'm looking at that and thinking of calcium ions and bromide ions. Br minus will be available here. Silver nitrate, so straight away I'm thinking, right, here we go. We're going to end up with silver bromide. So silver nitrate acidified with dilute nitric acid can be used together with another reagent. Another reagent, it's A-level chemistry. We know where this is going, don't we? When we get our silver halides, okay, we can identify them further beyond just their colour using different concentrations of ammonia. Okay, so let's read it again. So silver nitrate acidified with dilute nitric acid can be used together with another reagent to test for the presence of bromide ions in a solution of a medicine. Describe how you would carry out this test and state what you would observe. Okay, right, so what would you do? How would you carry it out? You'd add silver nitrate solution and then dilute ammonia. That's 1 mark. It's got to be dilute ammonia. Okay, right, for the second mark, a cream precipitate is formed. That's the silver bromide compound, then the cream precipitate. And then for the third mark, you need to say which is slightly or sparingly soluble in dilute ammonia. Okay, so that emphasis between dilute and concentrated ammonia in these questions is key. Okay, yeah, the next little error that tends to take place, this was a group 2 question, looking at why calcium has a higher melting point than strontium. Okay, right, so this is what we need to say. So calcium has a higher melting point than strontium because for calcium, the delocalized, i.e. the outer electrons, are closer to the nucleus, and therefore this attraction is stronger i.e. the nuclear attraction for the outer delocalized electrons is stronger. Okay, so remember that the melting point, the height of the melting point is all determined by the strength of the metallic bond. Okay, and the metallic bond exists because of the attraction between the nucleus of the metal atom and its outer delocalized electrons. So if the nucleus is nearer to the outer, i.e. delocalized electrons, okay, the force of attraction is stronger, so therefore the melting point is higher. Okay, next question. Right, okay, yeah. Right, so again, this was part C was the problem here. Again, it's the understanding of the reactions of dilute or concentrated ammonia with the silver halide precipitates. Okay, so the chemist suspected that the waste tank contained hydrochloric acid. State how the precipitate formed in test B could be tested to confirm the presence of hydrochloric acid in the waste tank. State what you would observe. Okay, right, so the tank contained hydrochloric acid, so that clearly contains the chloride ion, the Cl- ion. Okay, so we could test with dilute ammonia solution. Okay, and if silver chloride was present, then this precipitate would dissolve. Okay, suggest one reason why carbonate ions could not be present in the waste tank, because they would have reacted with the acid. Yeah, that's pretty straightforward. Right, okay, so again, it's this area. Do you know the test for the halide ions and their solubilities in ammonia? Okay, and here is the table. This is on one of the videos earlier. Okay, so just a recap. If I add silver ions to a solution containing the chloride ion, I get a white precipitate of silver chloride, which is soluble in dilute ammonia. Okay, if I add silver ions to a solution containing bromide ions, I get a cream precipitate of silver bromide, which is sparingly, i.e. slightly, soluble in dilute ammonia. Okay, but it's soluble in concentrated ammonia. So these words, dilute and concentrated, are very relevant at this stage. If I have a reaction between silver ions and iodide ions, I get a yellow precipitate of silver iodide. Okay, and silver iodide is insoluble in concentrated ammonia, but again, concentrated ammonia, that's the key. It's insoluble in concentrated ammonia. Okay, so there we are. What's next? Number 7. Okay, state and explain the trend in electronegativity down group 7 from fluorine to iodine. Right, so if you remember what electronegativity is, it's the ability of an atom to withdraw electron density from the covalent bond. Okay, right, so what forms a covalent bond? Well, it's a shared pair of electrons. That has got to come through in the answer. Okay, so what's the trend in electronegativity down group 7 from fluorine to iodine? Well, the trend is the electronegativity decreases, and the explanation is because we get increased shielding as we go down the group for the second mark. Therefore, there is less attraction for the bonding pair electrons by the nucleus. It's the bonding pair electrons, okay, i.e. the electrons that make up the covalent bond that we're interested in, not just the electrons. Okay, so for that third mark, you've got to make reference to the bonding pair electrons. Okay, part B. State what you would observe when chlorine gas is bubbled into an aqueous solution of potassium iodide. Write an equation for the reaction that occurs. Okay, so you're saying to yourself, is a halogen chlorine more reactive than iodine? Yes, it is, so it'll displace. So chlorine more reactive than iodine, so therefore it displaces it. We get some I2 produced, which is a black solid, but tends to then dissolve in solution to make a brown solution. Okay, so that's a nice little question. Okay, right, part C. This is another area that generally people just don't really know well enough. Okay, so, and it's a standard question as well. Okay, it comes up on nearly every paper every year. Okay, so identify 2 sulfur containing reduction products formed when concentrated sulfuric acid oxidizes iodide ions. So I'm looking at the reaction here between I- and SO4 2-. Okay, and straight away you're thinking, oh yeah, here we go, it's this table here. Okay, absolutely key. So this was looking at the reducing power of the halide ions. Okay, so chloride ions with sulfate ions. The chloride ions didn't reduce the sulfur in the sulfate ions at all. The bromide ions, when they react to the sulfate ions, they did reduce the sulfur in the sulfate ions from the +6 oxidation state to the +4 oxidation state in the SO2. But then when the I- ions came along, okay, they could reduce the sulfur in the sulfate ions, okay, to produce SO2S and H2S. So from +6 in the sulfur, +6 in the sulfate, to +4 in the SO2, to an oxidation state of 0 in the sulfur, to an oxidation state of -2 in the H2S. Okay, so I- ions were your strongest reducing agents. Okay, if you remember, very, very important table. Right, so let's use that now in this question. Right, so I'm reacting here concentrated sulfuric acid with my iodide ions, SO4 2- with I-, and we know that I- is a strong reducing agent. It's the strongest reducing agent that we deal with in terms of halide ions at A level, and we can get SO2 produced and we can get S produced. Right, write the half equations. So let's do it. Get a bit of paper. Okay, so I'm converting. I want to go SO4 2-, SO4 2- going to SO2. Well, like any half equation, I've got 4 oxygens on that side, I've got 2 oxygens on that side. Okay, so I need 2 H2O on this side to make sure I've got the right amount of oxygen. So 2, 3, 4, 4, I've got 1 sulfur, that's okay. But when I do this, then I've got 2 times 2, which is 4H plus. Okay, what's my charge on this side? Overall charge is 0 on that side. At the moment my overall charge on this side, I'm +4 -2, so I'm at +2. Okay, so therefore if I have 2 electrons, that brings that down to 0. Okay, so there you go. That's your SO4 2- plus 4H plus 2 electrons goes to SO2 plus 2H2O. Okay, next one then, if I want to convert my SO4 2- to sulfur, okay, 4 oxygens on that side, I'm going to need 4H2O on that side, which then 1 sulfur, 4 O's, 4 2's 8 plus 8H plus. Total charge on this side here is 0. I need to get this down to 0. So at the moment I'm at +8 -2, I'm at +6, but I need to get down to 0, so I'm going to add 6 electrons onto there. Okay, so there you go. SO4 2- plus 8H plus 6 electrons goes to S plus 4H2O. Okay, right, so next one, part D, write an equation for the reaction between chlorine gas and dilute aqueous sodium hydroxide. This comes up in the disproportionation of chlorine. Okay, and to be fair, this equation is straight out of the revision guide that we use. Name the 2 chlorine containing products of this reaction, give the oxidation state. Again, a disproportionation reaction. It's a very standard question and just something that you have to know. So Cl2 plus 2 NaOH goes to sodium chloride, sodium chlorate 1 and water, NaOCl, okay, plus H2O. So product 1, sodium chloride. What's the oxidation state of the chlorine in that? Well, that's +1, that's -1, so it's -1. Name of product 2, sodium chlorate 1. Okay, there's a bit of a giveaway in the name there, so the oxidation state of the chlorine is +1. So I'm looking at this here now, that this here contributes +1, that contributes -2. The overall charge on it is 0, isn't it? So I've got -2 +1, I'm at -1, so that must be contributing +1 to get it back up to 0. Okay, so that's how that works. Right, okay, the key videos then that really we need to have a look at again are trends in chemical properties of group 7 elements. Okay, and then also group 7 elements, the halides and their reducing powers. Okay, those 2 videos would be a good watch based on mistakes that have been made on these questions. Okay, so there we go. That's it for today. Thank you for watching. I hope that's been helpful. It's key to make sure that you take note of these errors, and don't forget to like and subscribe and click on the bell notification to stay updated.